Here we are discussing an example 9.3 in the textbook. It is perturbed circular orbit. So the problem is a satellite of mass m orbit the Earth in a circle of radius r0. One of its engine is fired briefly toward the center of Earth, changing the energy of the satellite but not its angular momentum. The problem is to find the new orbit. The situation is, here we are considering a satellite of mass m. It orbits around Earth and in a circle. So orbit around Earth in a circle of radius r0, and the situation is one of its engine is fired, okay, and briefly towards center of Earth, changing the energy of the satellite, and one of its engine is fired and its energy is changed, but its angular momentum did not change. So its angular momentum still remains constant. The problem is to find the new orbit. So here we have to find the new orbit because it's one of its engine is 5. So here we have to find the new orbit and the characteristics of the new orbits. So the energy diagram, here it is shown that the energy diagram, this is the energy diagram, and it shows the initial energy of the satellite is EI and the final energy is EF. And please note that firing the engine radially does not change the effective potential because L is not altered. We know that the expression for effective potential L by 2 mu r square, and L is constant. So its effective potential does not change. So this is the initial energy and this is the final energy of the satellite. This is the after firing its engine, this is the energy. And since Earth's mass me is much greater than the mass of satellite m, so here the mass of Earth is me and the mass of satellite is m, and when you calculate the reduced mass or center of mass, you will get the center of mass is approximately m because me is very much greater than m. Okay, so we can say that the reduced mass or center of mass is m itself. Okay. So if EF is not much greater than EI, and if there is no much difference between EF and EI, the energy diagram shows that R is never differs from R0. So if this is R, this is the distance. So if there is no change between EF and EI, the R0 will not change. It's approximately equal to the distance from here to here. So if both are equal, it's approximately equal, we can consider the radial distances R0. Here we are approximating U effective of R in the neighborhood of R0. Since R0 and R are almost equal, so we are approximate U effective of R in the neighborhood of R0 by this parabolic potential. Here this is the initial and final energy of the system. So this is a bound system. So the radial motion of the satellite is produces simple harmonic motion, or it is in simple harmonic motion. Small oscillations of a particle about equilibrium position about r0, so simple harmonic motion will be produced. The effective potential, we know that the effective potential is effective potential with C is equal to, let us take C as GMME. Okay, so this is taken as C, therefore the effective potential is equal to minus C by R plus L square by 2 M R square. Here it is M, it is the reduced mass. C is GMME, so minus GMME by R is the U of R, and this is the centripetal term. So effective minimum, it is at R is equal to R0. Effective minimum is, look at the picture, it is here, it is R is equal to R0. This is the minimum U effective, and the slope will be 0. Therefore d U effective by dr at R is equal to R0, it will be equal to 0. So C by differentiate this term once with respect to R, you will get C by R0 square minus L square by M R0 cube. Take the differential with respect to R, and this will be equal to 0. So equating this, you will get L is equal to root MC R0, and R0 is constant, C is constant, G M M E, and M is constant, therefore L is constant. And here it is said that the motion will be in harmonic motion. So these are you studied in the chapter 4 of this textbook, work energy theorem. This is a bound system. This is a bound system, and it oscillates in the boundary, and it will be harmonic in nature, simple harmonic in nature. So the frequency, we can find the frequency of oscillation of the system. Let us take it as beta, so it is K by M. K is equal to, this all you studied in the chapters 4. K is equal to d square U effective by dr square, and R is equal to R0. So you just differentiate this du by dr once more, this term once more, you will get this minus 2C by R0 cube plus 3L square by M R0 raised to 4, and you have found an equation for L. You substitute this equation here, you will get K is equal to C by R0 cube, and substitute for beta, beta is equal to root C by M R0 cube, and what is L is root MC R0, and you substitute for that, you will get this term as L by M R0 square. Just calculate all this, and so we have found that beta is equal to L by R0 square. And now we can find the radial position, that is the radial position or the R value of new orbit. The R value of new orbit is taken as R, and it is equal to initial radial position plus A sin beta t. Since this is the radial motion, this is an harmonic motion, so you can find the value of R in terms of a sin beta plus b cos b, sin beta t plus b cos beta t, and how I have omitted the term a b sin b cos beta t, since um, here we know that the initial position is r0. That's why we put the r0 here, and this is the initial position, initial radial position. And why we didn't add the term cos beta t, it is because at t is equal to 0, what will be the value of cos beta t? It will be 1, and r will not be equal to r0. This will be this. Here we have a term 1 plus r0, and that is not true. The initial position is r0 only. So that's why we omitted cos beta t. And when you use sin beta t term, you will have t is equal to 0, sin beta t is equal to 0, and r is equal to r0 initially. That's why we have taken a sin beta t term here. So here we have to find the new orbit, and for that we must eliminate t and express r as a function of theta. And for circular orbit we have just studied the very first of this chapter, theta dot is equal to L by mr0 square, or we can write theta is equal to L by r0 square into t. So this is the equation for the new circular orbit, and here L by mu r0 square is beta, so theta is equal to beta t, and from this we arrive in a conclusion that both the frequency of rotation and the frequency of radial oscillation is same. So comparing the equations for L and theta dot, we can arrive that L by mr0 square is equal to root of c by mr0 cube, and theta is equal to L by mr0 square t. So L by mr0 square is beta, so theta is equal to beta t, and also we can arrive in an equation that the frequency of rotation and the frequency of radial oscillations are same. So this is the figure for the original orbit and the new orbit after firing the engine. So both are in a circular shape, but the center is changed, the center differed, and the initial radius is r0, and or a radial position initially is r0, and it is changed to r0 plus a sin theta. So the path is changed for the new orbit, and it is varying according to a sin theta. So at theta is equal to 0, r is equal to r0, and also theta is equal to 180 degree, it is r0. You can see it from the picture, and a variation is according to the theta variation. It is maximum of 90 degree and also the 270 degree in the negative direction. So this is the perturbed orbit when we are considering the satellite is, the engine of the satellite is fired, and the new orbit is like the original orbit, but the center is changed. Here we have to number one thing is that we have taken EI is approximately equal to EF. That's why both are in same shape. So, okay, so here in this picture the center only changed and the path is same,